Welcome to the second review lesson, continuity. This should be a nice short one. I expect it could be done within 5 minutes, 10 on the outside. Continuity. So it's odd, but we might actually start talking about continuity by talking about discontinuities, things that aren't continuous. Hold on a second though, I'm gonna see if I can get rid of the controls. There they go. All right, so there are 4 types of discontinuities. There are what are called removable discontinuities, like these. Sometimes we call removable discontinuities holes. It doesn't matter if there's a value placed there or not. If there's a hole, it's a removable discontinuity. They're called removable because they can be easily fixed by filling in that hole. If I take a pen, and I fill that little spot in, all of a sudden this function becomes continuous. I can trace it without picking my pencil up. Without that filled in, it's not continuous. I move along, I run into a problem, I have to pick my pencil up and skip over that small hole. So continuous functions are when you can trace it without having to pick up your pencil. If there is a discontinuity, we can name them. That type of discontinuity is called a hole. This type of discontinuity is called a jump, pretty obviously, because you're moving along and then you jump up to the next spot. This one's called an infinite discontinuity because I'm traveling along, and it just keeps getting closer and closer and closer towards infinity. So that is an infinite discontinuity. This one happens to go towards infinity on both sides, but if it was on one side, going up towards infinity on one side and down towards infinity on the other, it's still an infinite discontinuity. The last type isn't quite so popular. We don't see this one a whole lot. You probably don't need to worry about it too awful much. It's called an oscillating discontinuity. It's when you have a function that's oscillating, meaning going up and down, but those oscillations end up going faster and faster and faster until at some point they're going infinitely fast. And there's some kind of break there, but you just keep going up like faster and faster oscillations. An example of this type of one would be something like sine of 1 over x. That would have an oscillating discontinuity at 0. I can't plug a 0 into there. But the closer I get to 0, the more those waves would go up and down, faster and faster and faster. Continuity at a point is defined like this. F of x is continuous at some point x equals a if and only if the limit as x approaches a of f of x is equal to f of a. In other words, if I go back towards these removable discontinuities, right now, if I tried to find the limit at this discontinuity right there, it wouldn't be a problem. The limit would be whatever value this is equal to. Like if I put some grid along here and I said this value is 3, then the limit is 3. But if I tried to plug that value in that value of an, I don't have anything out here. So the limit is 3, it's not the same as plugging a in. Same thing when I got a point up like there. If I put a point up here, then when I plug a in, I get that value out. Let's just call that 4, which is not the same thing as 3. However, if I bring that point down like that, then the limit of the function as I approach a is right there. The value as when I put a in is also right there, and that means the function's continuous. I can trace it along it. There's no break in the graph. So this definition just basically gives us a way of defining continuity. We know we're continuous if when we try to find the limit at a particular point, it's the exact same thing as plugging that point in. When I try to find the limit at a, it ends up being the same value as when I plug a in. Limit goes towards that spot there, a is at that spot too. I'm going to erase this just in case I save it later for notes, but that explains continuity. We're going to run through just a couple continuity problems and we will be done after that. All right, so find a value of k such that f of x is continuous for all x. So I've got a piecewise function here again. When I look at 4x minus 11, I'm not too worried about that because that's just a line. Lines are continuous everywhere. When I look at k equals x squared, I'm not too worried about that either because I know x squared is a continuous function and multiplying it by some k just gives me a vertical translation, a vertical stretch, if you will. So I'm not worried about that, but what I am worried about is right here at 3 when it switches. It's 4x minus 11 up until 3, and then it switches to kx squared right after 3. If this function is going to be continuous, that left-hand side needs to connect with that right-hand side so there's no kind of jump here. So what I'm going to do is I'm just going to check out from the left. From the left, I'll have the limit from the left specifically. Limit from the left as x approaches 3. Well, that I can find pretty easily with substitution. Take a 3 and plug it into there. I'm going to get 4 times 3 minus 11, which is 12 minus 11, which is 1. From the right-hand side, it'd be this function. So I can do it again, limit from the right as x approaches 3. I can fit all this here. We're just gonna do this so I can give myself some space. There we go. All right, from the right, I would use this, plug a 3 into the x, right? Because I'm saying as x goes towards 3, I can use substitution. I plug the 3 into there, and I'll end up with k times 3 squared, which is the same thing as 9k. And then I look at these and say, all right, from the left-hand side, I'm approaching 1. From the right-hand side, I'm approaching 9k. I want this thing to be continuous. So that means the value of k I have to pick is whatever it takes so that this value and those values are the same, so that the limit from the left and the limit from the right are equal. In other words, I want 9k to be equal to 1. Well, the only way for that to happen is if k is equal to 1/9. That is a value I would need k to be if I wanted this f of x to be continuous. Any other value I pick for k is going to cause a jump. The limit from the left would be 1, and the limit from the right would be some other number other than 1. Like if I put in a 3 for k, it'd be a 27, and since those aren't the same, my limit wouldn't exist. And then I would have a problem where the limit is the same thing as plugging the number in. All right, moving on. Very last problem, we got 2 problems here. It says list where each function is discontinuous and name the type of discontinuity. So when you're looking for discontinuities, basically you're looking for problems in the function. When I look at this, I know I have a problem when I'm dividing by 0. I can't divide by 0. If I plug a 3 in there, I'll have 5 divided by 0, which is undefined. There's going to be a discontinuity there. So here I know I'm discontinuity. I'm just going to discontinuous what I'm going to say the discontinuity is at x equals 3. When I plug a 3 in here, I'll be dividing by 0. As far as the type of discontinuity, you might remember whenever you try to divide by 0, you end up getting a vertical asymptote, right? Because like 5 divided by something closer and closer to 0 gets closer and closer to infinity. So the type of discontinuity that is an infinite discontinuity. Also known as vertical asymptote. Second problem here. Same thing, I've got a problem when I plug 3 in as well. I'm dividing by 0 and that's a problem. So I know right away I've got a discontinuity at x equals 3. It would be really tempting to say it's also a vertical asymptote. Same for the same problem here. However, I want to be careful about that top. If you factor that, it'll end up factoring into this. And the reason that's important is take a look at those x minus 3s. X minus 3 divided by x minus 3 is always, always, always 1, with the one exception of when I plug a 3 into there, I've got 0 over 0. 0 divided by 0 is not 1. 0 divided by 0 is undefined. So this function really just looks like 2x minus 1 everywhere except at 3. At 3, there's a hole. You might remember that we always have a vertical asymptote whenever you divide the denominator to 0, with the one exception of if that denominator can be canceled out by some factor in the numerator, in which case you don't have a vertical asymptote, you've got a hole. Holes are removable. You can fix those discontinuities. So the type is a removable discontinuity, which are also known as holes. All right, that was it. That's your lesson on continuity. There's a worksheet on Schoology. Good luck. As always, send me an email if you have questions.